Hi, I'm Duncan Woodbury, teamed with Neil Joshi. This is DeepMotion, a convolutional neural network for video frame interpolation. A video can be thought of as a time-ordered sequence of images, which we'll call frames. The frame rate of a video, or the FPS, is the number of frames which occur per second. The higher the FPS, the higher the resolution. Our question is it possible, using convolutional neural network, to generate an intermediary frame between every pair of subsequent frames in a given video, thereby doubling the resolution and doubling the frame rate? Video frame interpolation has many applications throughout industry, the most common of which is probably in modern TVs, which perform interpolation in order to increase the resolution of the video that they're displaying. There are also certain other special effects that are desirable in film that can be attained, such as generating an artificial slow motion effect. The entire implementation is built on the Python language using the Keras and TensorFlow deep learning libraries. The dataset initially used was the Kitty dataset, which is a dataset of 80,000 images made up of sets of time sequential image frames, pre-separated videos, used to train self-driving cars. This has the advantage of being rather uniform in terms of the objects that occur in each set of images. This has the advantage of using this data uniform in terms of the objects that occur in each set of images. Refined further using data pulled from the YouTube ADAM dataset. We used 150,000 samples from this database of 8 million categorically classified and labeled videos specifically for use in machine learning applications. To pre-process the data, the Kitty images are resized to 384 by 128 to improve the training network speed. YouTube ADAM presented additional constraints in the fact that since YouTube ADAM videos are MP4 videos, on the fly during runtime, we have to use FFmpeg to read the video as an array of images and sample frames.
So our network architecture is modeled off of the UNet architecture, which is used for biomedical image segmentation. It's basically the same network with a few minor changes. We have a different input shape of 6 by 128 by 384. We use a 6 because we have concatenated 2 of the frames into the same channel axes, and the output is just a normal image of 1 frame. The main part of the network consists of these 2 key blocks. So we have 5 blocks of 2 3x3 convolution layers with the filter size increasing on each of the blocks. And each block is followed by a 2x2 max pooling layer. And for the other set of blocks, we have the same exact thing while the filter size is decreasing. And then it's followed by a 2x2 upsampling layer. So we sort of have a symmetry in this network that allows us to basically have an interesting feature where we can merge the outputs of the first half of the layers in the network and concatenate them to the outputs of the second half of the network. So we can sort of maintain the fine-grained detail that the first few layers of the network have because of the large image output size, and concatenate them with the rest of the network in order to get the maximum amount of features. So in regards to our training configuration, we're using a special loss function, the Charbonnier loss function. It's similar to mean squared error loss function, but it depending on the value of epsilon that we set, we can have a threshold whereby if we go below that threshold, our loss value actually increases quickly. And so that can sort of converge training in a more optimal solution. We're using the Atom optimizer, which is sort of the standard optimizer these days for most training cases. So we utilize a dynamic learning rate scheduler where we start the learning rate at 0.001 and we track the training loss, and as it stagnates, we lower the learning rate accordingly so that we avoid getting into a local minimum. So in terms of our training in general, we trained over 153,000 samples in the Kitty dataset, which is close to 2 epochs over the whole dataset, and it took about 10 hours on a 980 Ti GPU. And after that was done, we fine-tuned the model over the YouTube 8M dataset. We went over roughly 80,000 samples, but because of the longer time of fetching live FFmpeg frame extractions from MP4 files, training took about 24 hours. So getting into some results here, we have the one of the images from our kitty dataset. And so this is the first frame in our triplet, and this is the middle frame that we will be predicting, and this is the last frame. So we take the first frame and the last frame into our network, and then we try to predict what the middle frame will look like. And here's just sort of a naive representation of what the middle frame would look like if we just blended the first and last frame together. And so you can see it looks very messy on the left there, but now if we set those two frames through our network, we can get a much nicer looking image that fairly accurately predicts the middle frame. And here's another example where we have the blended representation of the image and then the predicted middle frame. And comparing this with the actual middle frame, you can see there's quite a noticeable loss of quality. While the actual motion representation is still pretty accurate, the loss of fine detail is fairly significant, but it's still interesting to see how the network can accurately detect objects and move them relatively to where they should be in the middle frame, even if they're not finely detailed. Now here's an example from the YouTube 8M dataset, and so you can see the blended representation here. And then the predicted middle frame actually does a fairly good job. You can see there's pretty distinguished lines that sort of converge into the middle representation of that line. But once again, we see that the actual middle frame does have a much greater detail and clarity inside of the image. Here's another example of an image that we wanted to compare between an image that went through our model before we did fine-tuning on our YouTube 8M dataset and after we did that. And so we can see this wine bottle here with some text, and the text doesn't really show up well in the predicted output, but in the fine-tuned model it actually shows up well, which shows how our fine-tuning on a wide variety of datasets helped the robustness of the model in the end. And it wouldn't be a proper frame interpolation demo without some videos. So you can see with the motion here in the video, you can actually get a really good representation of how the algorithm performs. And you sort of don't notice all the tiny irregularities and the detail loss that you get from our model because everything is in motion that you don't really notice. And the fact that the interpolation is handled fairly well in terms of its tracking of certain elements in the scene is very apparent in the smoothness of this video. And while we don't have time to show you all the videos that we've recorded in depth, you can go to our code and check them out if you want to look at them further. And thanks for watching.